So I'm really happy to bring this speaker today. Nick Hurd is an excellent researcher, but first and foremost, he's a real good friend of mine, and we go back at least to 2011, which makes us both of a certain age, I think. We met in true academic style in that I was working on my dissertation, and I thought I had an original idea. I don't know, many of you have probably come across this where you thought you had an original idea. I did a little bit of literature review, and it turns out somebody beat me to it. And it turned out it was Nick. And so I sent him an email and said, hey, that's a great idea. I thought it was mine, but you're a smart guy for having it. And that resulted in a long-term collaboration. We've got papers together and patents, and I've mentored his postdocs and students, and I hope to extend that relationship here at Microsoft and do a lot of collaboration with Nick and Imperial College. So with that, we're going to hear his views on statistics and cybersecurity. Thanks, Nick.
Thanks, Josh. Thank you for the very generous introduction. That's it's not quite as he tells it, but it's very kind, very, very kind of you to say that. So thank you for the invitation. I'm thrilled to be here to talk. So the title of my talk is Statistics and Cybersecurity. So I'm a researcher from the Department of Mathematics at Imperial College in London, and also seconded out to the Harvard Institute for Mathematical Research. So here's the obligatory slide of people I've worked with in the work here. I'm looking forward to adding Josh's name in Microsoft the next time I give this talk. So the top line are my graduate students working at Imperial, and then Sylvia works at the ATI, the Alan Turing Institute, as a postdoc. Pat's a friend and collaborator at Bristol, and Melissa is at LANL, and there'll be lots of mentions of Los Alamos, or LANL for short, throughout the talk, and everything I have in terms of contact with them, which is all from Josh, so I'm very grateful to him for that collaboration, which has been a long-lasting and very fruitful collaboration, so that's all due to Josh. Okay, so I probably don't need to plug this point to you guys so much, but there's a general understanding, I think, by government and industry that data science techniques have some role to play in the future of cybersecurity defenses. There's plenty of data sources available that could help discover and prevent network attacks. At Imperial, our interests are in developing statistical or probability models for building models of normal behavior and detecting intrusions by seeing if there's outlying behavior with respect to those models. And the advantage of being able to do this is that we can sort of discover zero-day attacks by looking at people's normal behavior and looking for unusual deviations from those. So it could even be someone using legitimate credentials, but they may be stolen, therefore traversing in an unusual way. So these are the different data sources we look at at Imperial. Most of the things I'm going to talk about, it's about network flow data. So this IP address, talk to this IP address on this protocol, and some other data, particularly the start time is another thing I'll look at, so the timings of events. But we also look at other things as well, such as authentication events, so users authenticating on computers, whether or not they were successful and what time that happened. A bit of host-based stuff, so the events and processes, that's much more along the lines of that you guys probably look at, so that's a space we're just starting to work into, so a bit of that. And there's also the potential to do some physical type stuff like building access control, IoT, and so on. So a lot of the models I want to talk about are fairly simple. We want to think about high frequency data, and I want to just do thinning, so screening and triage, so like finding the interesting stuff amongst the bulk of traffic we have passing through our network. We want models that can be used in Hadoop if we can, and things perhaps that can stream. So there's lots of different ways we can think about analyzing our cyber data, and there's lots of different approaches. I'm going to focus on these three different ones. So you can think of these as heading down from the macro scale at the top down to a micro scale as we work down that bulleted list. So I could look at a sort of network-wide view of my network and perhaps use things like graph theory, spectral decompositions, community detection, and clustering. and also some high-level summaries for network oversight. So I'm going to do these in the reverse order in the talk. So I'll start with edge first. But yeah, so we can look at network level. We look at node-based models and build models of the processor a user or a computer runs, its connectivity, its pattern of life, what time it's active. Or we could go right down to edge-based models. So looking for, say, for beacons to specific IP addresses, some temporal dependence between edges, and typical packet sizes and things like that. So the point is that all of these could use useful cyber analytics. It's not a competition. We can look at all of these and come up with analytics and run them all in parallel, and gather them together is where we think we can gain strength. So we're going to have a whole bunch of analytics running and somehow try to combine them all. So hopefully getting a bunch of weak indicators and combining them into something strong. That's the idea. So we want to have lots of different views of the problem and combine them. So yeah, this talk is going to be a sort of summary of some of the work we've been doing in this area, some published stuff, some stuff we've already done, and the stuff we're currently doing now. So starting from the most micro level and look at edges. So an edge, between two IP addresses, say, I mean, to say that edge have an edge between X and Y, what I mean is that X has ever been observed to initiate a connection to Y. So I'm going to think about directed edges. All my graphs are going to be directed. So I have an arrow on my links between nodes. So a node will be an IP address. And yeah, you think of the edge as being this sort of fundamental, the primitive, if you like, of doing cybersecurity data analysis. It's not a node. It's sort of counterintuitive. A node seems like the sort of obvious fundamental, whereas actually from observing traffic, the edge is the primitive. The node is the union of all the edges coming from it. So the edge is the sort of the building block, if you like, for all our models. So that's the most micro level we can look at is a specific edge, the traffic from this IP address to this IP address. Okay. So in NetFlow, which is say what most of this talk is will be about, some edges will carry entirely automated traffic, some will carry just human traffic, and some will carry a combination of the two. Okay. So what I want to look at first is how we go about classifying edges as being either human or automated if we don't know anything about our network a priori. So one simple diagnostic you could have is that automated edges typically carry what I would call superhuman levels of traffic volume. So you could just threshold on that and say, okay, there's way more than a human could generate in that day. So that's got to be automated. So you could just do that. And I want to hold my hands up about that. But that's not always the case. And so what we want is some more sophisticated filters besides just thresholding on volume to say that's an automated edge that contains some automated traffic. So automated stuff is often highly periodic, corresponding to beacons for updates or keep alives. So we have a paper we did in 2014 where we scanned for periodicities in the data coming from coming on a single edge. So we looked at the periodogram after some observation time t, which can be efficiently calculated using the fast Fourier transform. So I'm going to explain a bit about what this formula does in a second. That second is now. So S hat of F, this periodogram, is effectively proportional to the squared magnitude of the resultant vector if I put each event onto the unit circle as unit vectors on the f to the -1 second clock. So that is, if I think about a particular frequency f, I'm going to imagine a clock of circumference 1 over f, and I just start the clock going and work my round down, and as events occur, I'm going to just drop a mark down and keep on going around, dropping marks down as the events arrive. That's what this does. If you forget this bit, this is uninteresting. That's just a constant, as it were. These increments of the process are being multiplied by this guy here, and that's essentially just plopping points down onto the circle in this way. So just backing off for a second, what we want to do is find surprisingly high levels of periodicity at specific frequencies, but we don't know a priori which frequency we're going to find them at. So I want to look at a bunch of frequencies and calculate this function here and see if there's any clustering of these points on these circles for any given f. That's the game. Does there exist such a frequency such that the points are all bunched if I put them onto an f to the -1 clock? So this is what my S hat of f looks like from my own computer's connections to Dropbox. Okay, so you can see a peak at around the 55-second mark. Okay, and so there are the event times projected onto such a clock, onto a 55-second clock. So you can see there's some bunching, but there's two sets of bunching. That's okay. There's been some sort of refresh at some point where they're all beaconing at one phase, and then there was perhaps a delay or a reboot or something, and then beaconing again at a slightly, still at the same periodicity, but a phase shift. But that's okay. If you look at the resultant vector, those are still on the same scale. Those blue points, I've got this massive resultant vector of just adding all those unit vectors together. Whereas if I just pick some other arbitrary period, so 43 was a number that came to my head, and tried putting that in, so that's them projected onto a 43-second clock. You can see them all just rather more uniformly scattered. There's still a bit of bunching, because that's normal. You do get multiple pulses for a single sort of event in a beacon sequence. You tend to get a bit of blurring in multiple events and so on. So I get a non-zero resultant vector, but nowhere near of the same magnitude. So that's the point. So that's what's driving this spike in S hat of F. It's that there is that fantastic bunching at that specific frequency. Hi.
So when you say a priori expectation on the frequency, I mean, are like everything between a nanosecond and 23 weeks, or like is there?
Yeah. Well, we only have data recorded to the millisecond, so I'm never going to find anything.
In principle, you can find stuff, at millisecond frequency, and then at like 3 minute frequencies.
Yeah, like a few seconds is common. That's possible. Yeah. Whereas if I go too big, then I get 86,400 seconds, i.e. a day, and that's just human again. So I'm kind of interested in periods which are somewhat less than that. Good point. Okay, so that's just to see what it looks like. So that's what. If I looked at all the traffic coming from my computer, the left-hand image shows a sort of time of day histogram plot of when my computer does its business. And you can see I've got this sort of big spike of activity at 2 a.m., which isn't, I hopefully in bed some of the time, so that's not me. And you can see that all gets sort of taken out if I filter out by doing this sort of processing. So 80% or more of my traffic was easily found to be automated by just doing this sort of filtering with really significant p-values on this test, which I didn't really say about, was Fisher's test using this statistic, the maximum of that function divided by the sum of the things. Okay, sum over all frequencies. I want to find a specifically high frequency. And using simple central limit theorem arguments under the assumption of a null model of a homogeneous Poisson process, these things would be chi-squared under the null. It's easy to work that out. And so you can get closed form or approximations of the p-values really easily, so you can actually quantify these things. So yeah, that's stuff we'd done a few years ago, so that's out there, and that's kind of a handy technique. So that's our sort of first go-to thing in terms of classifying an edge. But you can see even in the Dropbox picture, there are still a few edges, events that don't sort of fit in with the bunching, and it's kind of interesting to think about mixtures where perhaps I've got some human things as well as perhaps I've changed a file there or whatever. There could be some human mixed in with stuff, because you'll still get it, because even if I've got an edge which has a mixture of human and automated high.
For every human, you assume this is one person, or is it possible that there are multiple?
Well, I know this computer, it's mine, so it's probably one person. But yeah, but probably multiple.
No, at the same time. Is it possible that the edge is not just like between a single computer and, I don't know, a server, but behind this single IP point there are multiple computers?
So, that's a great question, and there'll be a bit later on in the talk. I'll talk about mixtures of individuals, so that'll be there. But I'm not being prescriptive about that. I just want to know: is it automated? Is it clearly periodic, or is it something else? But that's a fair question. But I'll come back to it. So yeah, if I've got a mixture of human and automated stuff, the automated traffic is always high volumes. That will dominate. So I will be able to say, okay, there is periodic. There's a periodicity going on this edge. But there could be a mixture, and so what current work is doing with Francesco is looking at looking to separate out and classify every single event and say whether every single NetFlow event is automated or human. So, for example, there's two ways in. One is I can look at these clocks. If this is the frequency I found, I can say, okay, well, this event here, it's not in phase with the rest of the beacon. So this is somewhat of an outlier from that. So that's one indicator of that being perhaps a human event, is it's not in with the bunched events of the periodic signal that I'm looking for. Okay, so that's one piece of evidence. Is it in phase with the beacons? And the second thing is, what time of day did it happen? Is it in the middle of the day or is it during the night time? So those are two slightly orthogonal pieces of information which I can bring together to do inference on an event by event basis. saying that there. So briefly, what we're doing then, we're looking at a Bayesian mixture model to learn the human and automated components of this mixture density that we think might be going on a given edge. So if I call FA the density for automated events and FH the density for human ones, I want to learn those two things. So just for simplicity, so when lots and lots of simple stats models, we want to do these things at scale. So we fit a wrapped normal distribution on the unit circle. So we rescale everything once we know our inferred frequency from the Fisher's test. We can rescale everything to the unit circle and put it on 0 to 2 pi. So we have an automated density FA for learning the mean. Essentially, what's the phase? Perhaps that should be a mixture distribution. We've got multiple phases, but at the moment it's just a single one. And for this example, that's fine. And we learn the variance of these beacons. So we want to learn the mean of the variance. So what's the phase shift and what's the blurring? Because it's always plus or minus a bit of time. It's never bang on. So I want to learn that for the automated part. And for the human thing, we want to learn the daytime, essentially. So it hopefully has some sort of structure like that. So for that, we have a step function density. So I assume it's just piecewise constant density with an unknown number of steps. This is a particular hobby horse of mine. I just love piecewise constant things. They're really easy and tractable to work with, and they are consistent. If I don't bound the number of steps, then asymptotically, as I get more and more data, I will find the density. So they're fantastic flexible forms. So that's why we use that for the density for the human stuff.
Nick, is there a paper for this?
Coming, yeah. So this is work in progress. So these are taken from the draft paper, which Francesco's waiting for me to read.
Okay.
So he'll be glad to hear this question being asked and get on with it. is the message. So that's the beaconing stuff. So that's our work in terms of separating out automated from human. Now moving on to human stuff, we're thinking about, okay, so the automated stuff is kind of easy to understand, it's periodic, and that's okay. But we want to build models of the human stuff better as well. So even human-generated network connections don't arrive as a Poisson process. They come in bunches. It's kind of bursty, which Josh opened my eyes to when I first met him in 2011. So that was a big blow. So we've been doing loads of stuff with Poisson processes. Mathematicians like Poisson processes. They're fantastically tractable, easy to work with, so they're lovely models to work with. But if they don't hold, it's just going to give us the wrong inference. So with Matt and other of my graduate students, we're looking at trying to model self-excitation. So looking at the counting process of events on an edge, which we've considered to be human, and still trying to learn what this sort of self-excitation that goes on. So the model we've arrived upon is this sort of non-parametric walled process structure. I've included a diagram below, which is misleading because this is the only relevant one. These are just other models we look at in the paper. So essentially what's going on is I'm saying essentially if Y is my event process, my counting process of events for this edge of interest, then I have some background intensity lambda and then some triggering effect here. So if these are my event times, then I look at how long it's been since the last event, t minus y of t. That says how long has it been since the last event. And these lambda j's are going to be some decreasing sequence with, again, an unknown number of change points. I'm getting piecewise constant array, but with a decreasing intensity going back down until eventually it goes back down to the background. And again, asymptotically, we should learn the correct intensity. If it's the right model in terms of structure, then we should learn it. So people tend to work with Hawkes processes when people are doing self-exciting models of point processes. So there, you sort of add up, every time you have an event, you get a boost, like an exponential style boost. So that's what's drawn here. So every time I have an event, these red crosses, I get a boost in the intensity. So we looked at those models. We looked at the walled processes again, which that just says how long since the last event rather than accumulating. Because that's the thing. So I think with this guy, you just get too much because NetFlow is so bursty. You get this massive boost. The moment something doesn't happen, the model's in a bit of shock or you've finally stopped. So the walled models seem to fit better. And this exponential isn't quite right. It's a bit, we can fit more flexible things. Obviously, this doesn't look so flexible in this picture, but asymptotically, you say we can fit however many steps we need perfectly in the end. So this proves to be the best model in terms of fitting the excitation that happens within the process. So it's a flexible model, and it provides us a consistent estimator. The asymptotic will get it right. It captures burstiness, and by capturing burstiness, we found it negates the need to fit a model for seasonality, because that should be the obvious thing. If it's a human edge, my intensity function should have some component of, well, what time of day is it? If it's the night time, I really should be concerned about that. But we found the burstiness is enough. people don't leave work the same time every day. So fitting seasonal models is something I'm starting to go off. We've done that quite a bit, but it's such a, to do it well, you'd have to have a really flexible structure on top of that. There's a lot of work involved in doing that. And we found for the simple models we were looking at for building in time of day, this was just swallowing everything up. If I've just done an event just now, I'm still at work. And the moment I've stopped, then perhaps it's okay. And so it kind of...
The other thing about seasonality is it's expensive.
Yeah.
So in terms of keeping a million models around, or monitoring all our customers, we have to keep these models for each user, say, and we have to have all these parameters for the time of day, right? And so it gets expensive from the computing perspective.
Yeah.
Great.
So you can see the performance of them. So blue is the homogeneous process. So if we did our best fit of a homogeneous Poisson process of the data, this is a QQ plot. Okay, so we want to have a 45-degree line. If I just try and imagine that the data were a homogeneous Poisson process, I get the blue line. The red is an inhomogeneous Poisson process where I've tried to learn the time of day intensity, and I barely get any uplift at all from doing that. Whereas the self-exciting models do particularly well, and this is why the black line is the walled one with the non-parametric intensity, and that's the one which is doing best, which is why we favoured it. So I think it's incredible performance. I mean, it's not my work, it's Matt's, so I can say that. I think it's I can't believe we can fit that so well. This is just predicting when the next event's going to be. So yeah, that's interesting stuff. So that's edges dealt with. Not they're fully covered, but that's all we've done on edges. So next up, nodes. So one level higher up in the sense of granularity. So we've done some modelling of destinations of nodes. So looking at the sequence of IP addresses, say a computer connects to. Really related to some work I did with Josh on port scoring a long time ago. So it's kind of the same model again. So here we think about sort of scoring every single event. So look at a node and see who it connects to over time, and scoring the surprise of every single event. Saying, oh, you've connected to that one, and so on. So really simple things. And then aggregating surprise using control charts or p-value combiners. I'm big into p-value combiners these days, which is quite odd as a Bayesian, but I quite like them anyway. So in 2016, we've got a paper where we looked at modeling from a server-based perspective. So I look at a server, and it has its own model of, okay, who's going to connect to me next? I have a probability mass function on the go of who I think, and which learns over time, who I think is going to connect to me next. So we look at the sequence of clients, X1, X2, and so on, which connect to a server Y. And we simply model as a multinomial, so nothing clever going on at all, with an unbounded number of categories. That makes it a bit more interesting. So imagine I don't know how the limit of my computer network. There could be arbitrarily many computers. I don't want to put it, so I could think about having a base measure on the names of my computers, which I think is quite a fun thought, and some measure of confidence in that alpha. And then from that, just from that simple Dirichlet process model with a multinomial, we get a p-value for every single observation. So you can think of alpha x star as the measure attached to observing the next event being on x. So you get a chunk of probability from the base measure, and then it's essentially just a glorified histogram, a count of how many times I've seen this client connect before, along with the base measure. So really simple things. So to score an edge, first of all, we just looked at all the connections from each unique client to the server Y, and found the minimum p-value of that, and that should follow a beta distribution up to some approximations at least, assuming independence and continuity and so on, it being uniform 0.1 and not discrete. And we transform those to p-values. We get an edge, a p-value for every edge. And so then from a node perspective, what we want to do is then combine all those. If I look at a client, I want to say, okay, what was the p-value I got for each of your edges? So for a computer here, which turned out to be one of the more interesting ones, this is from the Los Alamos network data. This is the p-values we got for all its edges. So loads of surprise going on. So this was one of the red team attack nodes, this guy here. So it was really easy to find. I mean, those data are so easy. There's no great glory in winning this, but it's just a nice demonstration of how we can do simple models and get well-calibrated, decent answers out in an automated fashion. So yeah, we use Fisher's method to combine to get a node score in the end. And those are fairly arbitrary choices of combiners. So a lot of my work since then has been looking at how you choose how you make a proper choice of p-value combiner. So I've done a paper on that.
Is that paper published yet? Or?
It is. Came out in Biometrica this year.
Excellent.
Thanks. So more interesting, that's okay, that's fine. I can look at just my surprise at going to edges that I've been to before or not and so on. But really we're most interested in new edges. So if a node forms new edges, I want to think how surprising that is, okay? So yeah, in the red team attack and the LANL data, there was a whole burst of new edge activity created by the red team. And that should be an easy way of detecting unusual behavior. So what we want to do is sort of understand whether new edge activity is odd for that host. Because the point is that different hosts form new edges at very different rates. Some make lots of new edges and some are much more consistent in the nodes that they visit. So there are different rates between hosts, and also we want to think about who the edge is being formed with. If it's a new edge, okay, well, who to? Is that the sort of node you ought to be connecting to, or is it the sort of node someone else should be connecting to? So we want to understand, yeah, what's the right sort of node for you to be connecting to, as well as understanding the rate at which you should be forming those things. So we've been looking at building models of these things. So again, we look at this as a counting process. We look at the counting process of new edges being formed. Okay. So if capital X are my sources or my clients, and capital Y are my servers and destinations, we want to model the new edge intensity lambda xy of t for a client server pair xy. So it's a new edge intensity. So if GT is my current graph at time t of all the edges I've ever seen, then I've got an indicator saying I need it to be inside, I need it not to be in GT, so it's in x cross y / GT, so it needs to have not been seen. Otherwise, this indicator goes to 0. I've got no intensity of a new edge there if I've already seen it. So that's all that first bit is saying. Make sense? Then there'll be some seasonality function, which I'm going to treat as a nuisance parameter and not do inference on. So that's sort of the recurring theme in this. We're just not doing that much seasonality modeling. We did a bit earlier, but that's all. And then some other covariates, which are to do with the degree, the out degree of X, the in degree of Y, so how much they make new edges, whether they're in a burst of activity. So this is an indicator, it's equal to 1 if my last edge I made was a new one, and this is equal to 1 if the last 2 edges I connected on were new. That further terms didn't make any difference in stuff we did, so those seem to be the good covariates. So whether or not I'm in a burst of making new edges, that's a good predictor whether I'm about to make another. Plus some mysterious last final term of some latent variable, which is going to characterize the attraction. ZXY is going to characterize the attraction from X to Y in some model we're going to build. So we had 2 versions of doing that. One is a hard thresholding clustering model. So we cluster clients and servers and have a bit like a stochastic block model. We say this type of client connects to this group of servers. That's a good fit. So we cluster up the clients and servers into blocks and say, okay, well, that block does tend to connect to that block. So you and them, that's okay, or that's more unusual. Or we do something more soft and do a latent feature model with an Indian buffer process prior and so on. So trying to do a much more flexible style of modeling, which is, and that actually turns out to do better. So that's a paper which is under review at the moment. So it's work we've done, but it's not out there yet. But yeah, that turns out to be the best thing for what we did. Okay. Here's a picture just to illustrate that in action. So these are the p-values that we obtained for 2 computers. This is for that same infected one again, looking at now from a new edge perspective, and just some other random-ish uninfected computer to give a less anomalous picture. So these are control charts, essentially sort of combined p-value functions over time, and here are various p-value thresholds drawn on, and we have to work out by Monte Carlo what they should be to calibrate these things, because some have more events than others and so on. But on a p-value scale, these are now the same, and you can see that here we go way down in low p-values in terms of the new edges we're making here, whereas for the uninfected one, it makes new edges, but they're okay. They're not surprising either by the rate or by who they're with and so on. So that's it in action.
Nick, is this model adaptive? Is it learning over time, or?
I'm going to say, I think so. I've written it as a time-varying covariate. So I think the way we did it was we have to read data in chunks and update the model over time, and it seems to work out easier. Reading all the data in is a bit problematic for us in fitting this model, so we tend to just take a subset and just learn the network and then bring some more stuff in and so on. So I think so.
Okay.
But Sylvia Metelli has done all the hard work for that, so she'd be the person to actually be able to say, no, it's not, or yes, it is, or it could be, or... So that's quite a nice general, this sort of new edges or unlikely edges or something is a nice general construct. We can look at different things. We can look at surprise in the sequence of processes executed by a computer and measure the accumulated surprise in those, or in data fusion combining host processes and network level things and sort of getting scores for each of those things. So that's currently what we're doing under the data-centric engineering program at ATI. And with Josh in the past, we've looked at port scoring, modeling how unlikely using different services is. So yeah, lots of applications of such simple models in cyber. And then finally, a whole graph perspective. What am I doing for time? Oh, I've got ages. So yes, this is the very sort of highest level we could think about taking. So this is joint work with Pat and Francesco. So here, yeah, we want to look at the full graph and look at if we can learn underlying structure in the graph. So we're going to consider a binary adjacency matrix. I'm not going to think about counts just yet. Think about the binary directed adjacency matrix AT for my entire network, such that AT ij is equal to 1 if and only if I is connected to j, which I'll write that way, by time t. So here's just a cartoon graph of what G of t looks like, perhaps that 1's connected to 2 and 2 hasn't connected to 3 and so on, and look at that binary representation of that graph. So that's the adjacency matrix that I'm talking about. So yeah, a low rank approximation of this thing, so this is what I've observed up to time t. If I take a low rank approximation of AT, such as, or some Laplacian style transformation of AT as well, could be that. That can provide, it's a bit like building a statistical model. If I take a low rank approximation to prevent overfitting, if I'm taking a low rank, if I take a full SVD, I just recover the full matrix again. I don't have a model. I'm just saying, okay, I've seen this, and it's if I've seen it, then it happens with probability 1, and if I haven't, it happens with probability 0, so that's no good. Whereas if I take a low rank approximation of that thing and do some, it can be difficult because you go outside of negative and greater than 1, so you do some sensible sort of treatment of that estimate of A of t. You can think of that as being like a model, being like a prediction. So we can do estimation and prediction using this thing. So yeah, we think about SVD a lot. So A is approximately A hat of k, in the sense that if I do SVD and get A hat of k, that's the closest k-dimensional rank k approximation of A in the Frobenius norm. And essentially that gives me two matrices of vectors in k-dimensional space, so that if I'm thinking about clients and servers, say, every client and every server each gets a position in k-dimensional space. And even if those are the same computer, they'll still get one position in client space and one position in server space. That's the way we've treated it. So the ith or jth row of uk or vk respectively provide a sort of notional latent position in k-dimensional space for that client or server. And so, pretty pointless picture, but I guess what I'm interested in is be able to look at an adjacency matrix. This is like an observed adjacency matrix, which have mostly zeros, but the occasional ones scattered around. And what I want to do is find that unlikely one, that one which sort of glares out the pictures that shouldn't be there compared to the rest of the structure of the graph. That's the sort of game we want to play, either in prediction for the future or just looking at my graph and saying, oh, that one shouldn't be there. That's the game. So some work we've done in that direction was with Melissa from Lanley, and Francesco is now carrying on that work, where we actually looked at the non-binary version, where rather than just ones and zeros in this thing, instead in the ijth position, I've got the number of connections I've seen up to time t. So 0 if I've never seen it, but otherwise some non-negative integer, positive integer if I've seen the edge. So it's a bit of a decision whether you think is informative to see how many times a client is connected to a server. I mean, sometimes there might be a bit of overkill in that signal, but on the other hand, you're getting some sort of sense of preference, and not all edges are equal. And if I go to this edge, this server a lot, then perhaps that's an important server to me, and I want to think of it as a recommender system type problem where this sort of client really likes that sort of server. So that works is taking that approach. So we have a Poisson star model. So my adjacency is now count. So we have a Poisson star structure. But again, this dot product idea where I have latent positions for both the client and the server, or in this case, user and process, or user and computer, the same ideas. And there was some sort of clever prior structure so that we sort of shared some information between edges for the same user or for the same server. So you get the idea of busyness, like this user does a lot or this server gets a lot of traffic, and so we have some sharing between edges so that it's not completely free. So we had a p-value for anomaly detection given by the upper tail probability of the count. We see like how fancy getting as many as we did given this Poisson model. And then use Fisher's method, similarly to before, to combine edges to get a score for users or clients. Whereas now we're currently extending this work, which I was talking with Josh and his team earlier about incorporating known groupings of computers and users with unknown latent factors. So I could know something about particular users, say, okay, this user is in this department and so on, and so therefore there should be some natural grouping and some similarities. So I'm trying to find network structure, and if I already know some information about that, I should be putting that into that model, arguably. So we're looking at how to build those things in as further factors in this model, but it's the same framework. Now to revisit the question, so I was asked the question earlier about whether I've got more than one human user on a single edge, which certainly is an option I'm interested in. So we can think about the network traffic flowing from an IP address as being a mixture of multiple individuals, each exhibiting their own mixtures of behavioral norms. So I can think of the traffic coming from an IP address as like a mixture of mixtures even. So it could be different users, like a family of users all using the same IP address, and within that, different devices, like an IoT style thing. There could be all different sort of physical devices making network connections, and also computers and other things. So all sorts of, and different tasks as well. So all sorts of different mixtures you can think about going on. So generally, I want to think about mixtures or mixtures of behaviors. And I find it a very interesting research problem, but really hard to think about, is it possible to actually detangle that mixture? If I observe an IP address for long enough, could I infer how many people are using it, which devices, which types, which users are active at different times, which behaviors there are when they are active, and so on. Those things that feel they should be eventually observable, because if just taking the user example, they won't all be active all the time. They'll sort of come and go. And so if you could see the repeated structure temporally come and go over time, in principle, it should be possible to detangle that and say, okay, I can see those sort of connections happen in blocks of time and they stop and they come and go. So this should be possible to detangle, but it's really a really awkward inference problem. So yeah, I see this as like a sort of topic modeling problem. If we can do that, it's great because we could build better models. If I could say, actually, this isn't just a single homogeneous thing, this is actually a mixture of lots of different things. And if I could understand what those things are, then I'd be in a much better place to build good models. So yeah, we see it as like topic modeling, so which is a sort of idea in text analysis where I take a sort of corpus of documents and count how many times word appears as a bag of words representation, and think, okay, each document is made up of a mixture of topics, and those topics have distributions on words. That's the usual thing. So either it's about cats or it's about microwaves or whatever, and there'll be a different lexicon of words that are used for each of those different topics. But a priori, we don't know what the topics are or their word distributions. We don't know anything, but people still try to do that and try and infer what the topics are automatically. They try to draw them out. So that's a very active research area in computer science as well as statistics. So yeah, we see it as an analogous problem in cyber. So if you look at the traffic from an IP address or a user, then we could think about, if we think about an IP address, then the topics could be a user. So the different users could be each be seen as being like a topic, or their behaviors could be seen as a topic, and the IP addresses that those users or behaviors visit would be like the documents. Those are the topics, and the documents would be like a chunk of time of say 1 day of traffic. So yeah, we've done some work on that. So we did some initial, very, very low-level efforts at that, which is there, but that was a very easy problem. In trying to scale this up, it's really hard. But yeah, Bayesian non-parametrics is the standard way of looking at these topic models, and they allow potentially infinitely many temporally occurring and maybe even time-varying topics. There's so much you could do with this sort of stuff. So this is joint work with Jinyu Zhang, another of my PhD students, and she's doing really well, I think, considering. So this is an example data set we're looking at. So this is real data, again, from LANL. So let me get this right. So each row is a day of data. So it's 10 days of data, and these are 32 different computers being connected to. So, and each block corresponds to a true user. So this is user 1, user 2, user 3, user 4, user 5, and this is and the colors show how much they connected to each of these computers on each of the 10 days. So what we do is then take those data and smash them together, just because we make life difficult for ourselves, and then see if we can unpick it again. That's the game. Can we sort of infer just by putting some sort of ideas of sparsity? We think we don't want topics which visit all the computers. We want to have some idea. Okay, there's some sort of purity of these topics. So if I have a fixed behavior or a user, they don't visit all the computers. They have their favorites and they go to those. And we push that into the models. We have ideas of sparsity and some sort of temporal dependence. There should be some link over time. So you see the contiguous blocks of connectivity. And so we push that into the model as well. So we're still getting stuff wrong, but still it's great. We're getting some recovery of some of the sort of shapes here. So Jinyu's never happy with these, which I think they're not bad. We're not there yet, but it's sort of starting to be able to untangle without knowing anything, trying to untangle the mixture. It is up to the viewer to decide whether they think that's good or bad, but I think that's not too bad. Okay. Yeah, so I think that's, on the difficulty scale, I think that's the hardest thing we work on, because I think it's just, to do it at real scale, I think it's going to be really problematic. And finally, I'm going to talk with a bit more length about some stuff I'm doing on change detection. So this is work with an MSc student called Carl, who's starting as a graduate student in October. So he's looking at this stuff too. And it's also some work I'm doing by myself on changepoint analysis. I'm going to enjoy talking about that for the end of this talk. It's my current favourite thing. So finally, it just for a sort of overall look at our network, sort of outside of the graph and so on, it's just kind of just to look at traffic volumes, just see, okay, from Imperial or LANL or wherever we get data, is there an unusual spike in a particular port or from particular packet size or something? Is there some thing we can, I'm just want to count everything. I just want to count everything going through our network and say, is there something unusual going on in those counts? That's kind of, I feel like we ought to be able to do that. This is the most basic detector thing we should have on the go. We should have some situational awareness of that going on. And so the motivating problem, if you like, is WannaCry. Okay, so these are our data for the whole of 2017. So this is from Imperial's network. These are the counts of the number of NetFlow events we recorded on the three most commonly observed ports over 2017, port 445, port 443, and port 80. So port 445 is sort of the new kid on the block in this graph, in the sense it wasn't the most popular until just before May 2017, which was, of course, the time of the WannaCry attack, which is the biggest cyber attack to have hit the UK so far, at least, affecting the NHS and various industry and academia institutions, although Imperial hasn't been listed as one of them, but certainly we've seen an incredible spike in 445 at that time. And we ought to know about that. We shouldn't just be seeing that on Twitter or something. We ought to have seen, even here, right? I mean, something's really happening there. We didn't have to wait till the actual sort of outbreak thing to know that there was a gradual sort of uprising of the use of 445. Maybe there's for legitimate reasons, but we ought to at least have some some situational awareness of these sort of things going on before it goes sky high, and we still, if we're not counting things, we still don't even know. As long as our network's working fine, we don't really know. So that's kind of the motivating picture. So I want to be able to find peaks like that. Okay. But it's not just for ports, so it could be for services, but it could be other things like traffic volumes or data volumes or geolocations. Have I got more traffic connecting to IP addresses in location X or something? There's lots of different things I might want to count, and I really don't want to put a limit on that. So I'd like to be able to count lots of different things and model them in a flexible way and look for change points. So this is a graph that Carl's made, which is very pretty, looking at just a week of data for Imperial's network, looking at different ports. And these are some change points he's fitted. So he's an MSc student. It's excellent stuff to have done this, so Bayesian change point analysis on these multinomials. And so one is nice. It's nice pictures, and you can sort of see why change points are happening and so on. So he's looking at both changes in volumes and changes in the mixture. So he's doing a sort of marked change point thing where we look to say, okay, there's a change point and it's a change in the mixture, it's a change in the volume, or it's a change in both. So we classify the changes. The change points come with marks, and we fit that marked change point model.
Sorry, the mixture is the mixture of ports being observed?
Yeah, so what the various relative frequencies are, and then there's the overall height of the bar is the volume. So we're looking for changes in, so he has this sort of way of encoding it. So plus, I think, is a gain in volume. X is a change in, plus is a change in volume, and X is a change in mixture probability, and a star is those two on top of each other, so both of those things. So that's nice, and you can look at this, it sort of makes sense. But the other takeaway from me is that we've got an awful lot of change points, and I don't really want to be getting that alarmed that often. That's 1 week. So I don't go, oh God, everything's changed, and it's changed again, you know. So there's only a certain level of amount of surprise I'm willing to swallow. And this is it. So I guess that's this wretched seasonality problem again. Human behaviour is so annoying. If everyone would just do the same thing all the time, just not go to bed or not change the clocks or anything, just do everything constantly, everything would be so much easier. But they insist on having varied lives and going to bed and all sorts. So. And for looking at ports, that manifests itself in very different ways for different ports. So you can see port 443. I've got these. This is pre-WannaCry. WannaCry sort of messes things up even more. But even so, if you look at seasonality pre that in 2017, really big sort of weekday spikes for port 443. Less so for port 445, and so on. These are some of the more popular ports. Yeah, so there's all that sort of level of variation going on all the time. So if you've got these relatively different changes, then if I just start looking at those multinomials, I'm going to keep saying, oh God, suddenly port 443 is really popular, and oh, now it's not again, and so on. We're just constantly surprised over and over. And I don't want to get involved in modeling seasonality, as I've said, because no 2 weeks are the same, and there's always there's gradual drifts going on over time. I can't just look at last week; it's not the same, and there's all sorts of different things going on. So I'm going off fitting seasonality function instead, trying to build robust models that can just say, okay, let's just not get excited too often. Change point models. So the idea of a change point model is we rely on, we're trying to partition up, we look over time, we're looking through time, observing a stream of data. Essentially, we want to just chop it up into segments, chop the patches of time into segments, and we tend to fit really simple models within each segment. And then, therefore, when I've fitted these piecewise in segments, then the overall global model is therefore somewhat more complex because I've been able to fit a local model, and I learn where to fit the cuts and so on. So it's they're essentially a way of building a complex model with lots of little ones sort of concatenated together. And often the model we fit is an oversimplification, and so we get more change points than would be preferable, like in the figure I showed you. So you can model at seasonality, and that's certainly one alternative. But as I say, no 2 weeks are often the same, and building the models is labour intensive as well. So it's just an extra modelling problem to have to face whenever I want to count anything, because they don't vary in the same way each time. So this is just work I'm doing by myself. It's just looking at modelling data with change point segments where I'm going to admit the model's probably misspecified. And look for clear discontinuity for a change point rather than a gradual drift. So this might look like a bit of a hack, and maybe it is, but I'm kind of really enjoying working on it, so I'm going to tell you about it to finish my talk. So a quick review of Bayesian change point analysis. So tau is going to be my vector of change points, so it's unbounded. If you think about a data sequence that's going on forever, so I'm going to learn a sequence of change points, tau 1, tau 2, of increasing in time change points, which are unknown, and they correspond to the change points of a piecewise deterministic process theta of t. So my parameter of my model is going to be called generically theta, and it varies over every single time step, but it's constant within any segment. So for two neighboring change points, for any t within that, this piecewise deterministic process theta t takes value theta j. So it's just a fancy way of saying I have a parameter that changes at every change point. Okay, so theta j is the parameter for the jth segment. Okay, and so the usual thing is for Bayesian, we have a Poisson process on prior for the change points, and we try and learn them given the data. So suppose I observe, I'm going to think about discrete time, but actually what I'm describing actually works in continuous time, which is really nice, but I'm not going to talk about that. I'm just going to talk about discrete time. So I'm going to observe a sequence x1, x2, up to xn. So they could be these counts, or multinomial counts, or whatever. They could be just some data-driven thing. And I have got a model P of xt given theta of t, okay, where theta of t is going to be one of these piecewise deterministic processes. So Bayesian inference on tau is particularly tractable and doable if I assume conjugate independent priors for the parameters theta j, okay, or priors which can at least be well approximated by those conjugate and independent priors, in which case I can use the conjugate prior and then do some importance sampling and everything works out fine. So we tend to like looking at conjugate priors when we can get away with that. Because then those parameters can be integrated out and we obtain a marginal likelihood for all the data we've observed given the change points, which typically factorizes. There are examples like autoregressive processing where this isn't the case, but typically I'll have a factorization that looks like this. It's a product over segments k of the data, the marginal the joint distribution of the data within that segment. Okay, a product over segments of the probability of the data within each segment. So that's the sort of thing we're after, where I've integrated out theta out. So I've got for each segment, so I've just got a marginal likelihood for those observations within each segment, and then take a product over the segments, and I'm done. So that's the thing we're normally interested in working with. So that's very standard. So here's an example to make it concrete. So suppose within a segment I've got a gamma distributed rate. So for theta, which is so for a single segment, I imagine that theta 1 for the first segment, it follows a gamma distribution, and then within the segment, if I suppose I've got n things in the segment, then x1 up to xn are assumed to be IID Poisson theta 1. That's a sort of typical, so a nice conjugate prior for theta. That's a typical Bayesian model for the first segment of a change point model. Okay, so that's the conjugate prior, and I can integrate theta out and get a marginal likelihood for x1 up to xn. So the first, I think, interesting non-intuitive observation to make about this framework. So I draw a single theta and then draw x1 up to xn IID from Poisson theta. So I think, interestingly and slightly paradoxically, this sampling scheme is equivalent to the following dynamic theta strategy. So here I've got the same theta for the whole of the segment, and that's how I described it, the piecewise deterministic process. But actually, in terms of likelihoods, in terms of the generative scheme for the x's, this is equivalent. Just draw theta 1 again from gamma AB, and just draw x1 from Poisson theta 1. Then I redraw a new theta from the what would be the posterior of theta given x1. That's what that looks like. And then draw x2 from Poisson theta 2. ... Eventually drawing theta n from that posterior, and then xn from Poisson theta n. That gives the same joint distribution for x1 up to xn as this, which I think is really something really cool about that. I mean, and it's just basic stuff in a way. It's just Bayes theorem, whatever. But I think that's really elegant. I think that on the one hand, I've got a fixed theta for all the time in x1 to xn IID from Poisson theta 1. And in the second case, no, just x1 from Poisson theta 1. Now draw another theta, which is influenced by x1 and x2. So that's kind of an interesting, I think, observation on its own right. But there's a point to making this observation, is that I could start messing with this. And rather than doing this, I could do something a bit different. So in the back of Bayesian theory, Bernardo and Smith, you invent the marginal likelihood of these things. If I've got a Poisson distribution with a gamma distributed parameter, we can look up the marginal likelihood, and this is the form. It's a very nice, familiar form to those who do Bayesian conjugate models. And you can think of this thing as actually, it's really nice, you can think about this joint distribution as obviously, it has to be the product of the predictive distributions. Yeah, I can write P of x1 up to xn is P of x1 times P of x2 given x1. And this is just just probability theory. And so these things come, so that's what that looks like. I think of it as a product of n terms, and they're just all cancelling out all the time. And just the predictive of one thing is the denominator of the previous step and so on. So all the time, so you see this go up to I minus 1, then go up to I, so then the next of the loop from I equals 1 to n, these guys will just cancel out with the next, this guy will cancel out with the next one in the loop and so on. So you can see they all just cancel out and I get a very simple form for the marginal likelihood. But that's essentially what's going on if I think about it from the predictive distribution point of view. And Dayfonet's representation theorem means that it has to be this way. If I want to have exchangeable observations within a segment, which is what I'm generally thinking about things being IID from some theta where theta is drawn from a prior, that Dayfonet's representation theorem says if I want exchangeable observations, then that has to be the format. It has to be, this structure is exactly what it has to be like. Okay, but I guess my point is, what if I don't want exchangeability? What if I know my model's wrong? I know the data aren't exchangeable. I know, say, for example, there's some drift going on over time, some slow level of drift that I don't really care about, and I don't want to bother modeling it. I just want to absorb in the fact that these data aren't exchangeable. I'm more, I'm looking for continuous things rather than IID. So I'm willing to sacrifice exchangeability for model robustness. That's the argument I'm making. I think I'm more likely to be like the previous observation than I am the one at the start of the segment, because I don't really believe that it's IID. It's an underspecified model. So, yeah, we can break this full conditioning. So, for example, rather than doing the product of the predictive distribution like I'm supposed to, up to I minus 1 from 1, I can think about defining an alternative probability distribution on x1 up to xn, which I've indexed with k for a given integer k, as I'm defining it to be the product of, from I equals 1 to n now, of xi given not xi minus 1 down to x1, but just for the last k. So I'm just essentially windowing to the last k. Okay? And so I can still write down what the marginal likelihood would be under this formulation. So if I have this k window, say actually I only really depend on the last k rather than everything in the segment, I'm just like the last k things. Okay, then this would be my marginal likelihood. So that's great. I can still write down, integrate out parameters. I can still write down the marginal likelihood for my which is a bit messier, but I can write it down. But I don't know what k is. I don't have any. I'm not trying to be too specific about that. So I want to average this thing over some prior q on k. For example, the thing I've implemented in the work is geometric. I've got a geometric prior. So if essentially I'm here at time t and I'm looking back and saying it's a Bernoulli trial, looking back into the past, there could have been a change point with equal probability at every step back from here, but truncated by where my inferred change points are. So my change points are going to take on that interpretation. Yeah, so I'm jumping the gun ahead a bit here. So yeah, my joint distribution for x1 up to xn for a given prior measure q, which is going to be just geometric, is then simply this thing. So I'm just going to sum over my geometric distribution for k of these things. So I can write down the marginal likelihood for a given q, which is discrete, so it's fine. And to go back to that point I was making about the sequential thing, whereas I was saying, x1 up to xn being IID from Poisson theta, where theta was gamma, and I said, okay, that's the same as drawing theta 1, x1, theta 2. This is what this looks like. So it's saying, okay, for the nth one, theta n is drawn not from j equals 1 to n minus 1, but from j equals n minus k to that. So you're constantly redrawing theta again, but theta based on the last k rather than everything, and then averaging over k.
Is it possible to fit an ARIMA model to this time series of thetas?
Sure, that's exactly the thing I don't want to do. I want to do something really, really simple. But yeah, exactly. If I was a proper time series guy and actually wanted to learn the relationships going on, I could fit a separate ARIMA model for each thing. But I'm thinking about doing this over all different sorts of things I want to count in cyber. And I don't want to be going down that road. I mean, perhaps I should want to, but I'm interested in running really simple models where I can integrate every parameter out and just get marginal IPs. Just
the reason is that the ARIMA model gets expensive.
yeah. So I guess that's the point here. Is I'm trying to develop a generic change point tool that just can deal for temporal trend without any structural modeling at all. Just to try and get robustness. So taking the very simple change point models and tweaking them a bit so that they're more robust. That's the idea. But that's a very, very fair question. Yeah, it's like the opposite of what I want to do. For good or bad. Yeah, so I think that's the interpretation of this slightly sort of twisted model. Is I'm looking at there may have been a change point at any time in the past where that time follows a queue, this distribution queue, my prior of when I think the change point would have been, truncated by the change points that I do infer. So for a given fitted set of change points, what I'm saying is when I'm looking back, I think there's a geometric prior of how long it was since my last change point, but there definitely was one there. That's kind of how it goes. Therefore, these things in my mind sort of take on the interpretation of definite change points. They've really got to do a lot. They have to be, because I'm allowing some sort of possibility there could have been a change point anyway, even within a segment by this K. So this is what it looks like to simulate. It's a really nice place to start. So this is Poisson gamma again. So you can see the gamma parameters I'm using here. So a very small alpha and beta. So K equals infinity. That's just the normal model. So IID, and I've got a single change point in all these pictures. I've got a single change point at 200. So IID data in each segment. So that's what it looks like. So with an intensity drawn from a gamma with those values. Now I'm just going to change K to some different things. So this is what K equals 10 looks like. I'm just drawing from that model. K equals 5, and K equals 1. And then you see, you get some sort of temporal trend. So this drawing from the model gives me stuff with temporal trend, and that's what I want. So it's just a really cheap, naughty way of getting temporal trend without actually modeling anything. Just putting a geometric prior, essentially, is what's doing it. And I'm now going to change the gamma parameters. And why is that? The larger I make these guys, the more they're ignoring the data anyway. So the more temporal variation, the more I'm like drawing from the prior all over again, so the more temporal variation I'm going to get. So I'm now going to try bigger. So there's IID again, but with now a bigger alpha and a bigger beta. So okay, so that's K equals 1 with this bigger alpha and beta. So you can see there's all sorts. I mean, I kind of like this because this is no way a record value. This change point. There's no way like oh that's odd. If I was looking at this in a change point analysis, assuming exchangeability, there's no way I'd have fit a change point here, right? Because it's right in the heart, close enough to the heart of what I've already seen that there's just nothing to pick that point out. But there is this discontinuity. And so looking at it with something which accepts it's a temporal feature, then you find it because it's from the model. So obviously I'd find it that way, and I do. And so to finish, this is what these ideas look like when fitted to those port 445 data that characterize the WannaCry attack. So that's what I got just by running Bayesian change point analysis on the count, just looking just at port 445, just looking at treating them as Poisson, where I end up fitting change points. As I say, it's just too many. Whereas I'm claiming this is a more parsimonious representation of what's happened to this initial boost here, and then just before the attack, this boost started happening again here, and again here it really jumped up and so on. So my feeling is I really like this green picture compared to this red picture, but maybe that's because I'm biased because I really like the work. Yeah, so I'm calling that robust change point analysis. So conclusions. So what I've been trying to argue is that statistical methods provide a framework for automating the detection of significantly unusual cyber behavior. They can be formed at different scales, ranging from edge level to full graph analysis. At each level of resolution, the models will typically be underspecified due to the complex nature of both human and automated network traffic. So like, for example, when I was looking at the Fisher's G-test, looking at the beaconing stuff, and I remember I had that stuff on the clock and so on, able to quantify using chi-squared type things, the significance, getting a p-value out about the being significant beaconing compared to a homogeneous Poisson process. Well, no one ever thinks there was a homogeneous Poisson process going on in any of this, so that's a terrible null model, and so, again, underspecified models, but nonetheless, it's a good enough baseline null model that things which are significantly different, the more significantly different they are from that, the more like beaconing they are. So even though I may not be using the most perfect statistical models, the probability calculus is still giving me a coherent scale for prioritizing the most significant looking beaconing things, even if the numbers themselves aren't quite right. Okay, so that's kind of the argument, I think. So it gives me a coherent scale, but I'm not saying I necessarily believe every single p-value. But for that reason, much of our future work should be concerned with identifying robust anomaly detection methods through a combination of the sort of robust models I've been championing at the end there, trying to sort of be a bit more open to saying, okay, I think I probably misspecified this, and so therefore I want to be robust. And more importantly, combining evidence, doing data fusion, combining evidence from different tests, from different data sets and so on, so that I can synthesize multiple weak signals into a strong signal, so that if I'm combine robustness, which will sort of perhaps weaken my signal, if I can then combine lots of things, I can still get strength again. So it's just a list of a few papers I mentioned, but thanks for your time.
Questions for Nick?
Yeah, I'm not sure if my understanding is correct, but the way you compensated for not taking into account the seasonality is by generating the new lambda from the previous time step. Is this the idea then?
For the thing at the very end?
Yeah.
Okay. From the last k things, where k is unknown, and average over a
Oh,
measure.
so you do take it.
Yeah, so k has some prior measure.
So on the net flow stuff, I mean, there's I mean, this is going to be a difficult question to answer, but as you go from organization to organization, do you have any sense of like how much retuning and retweaking? Los Alamos is one thing. If you went to a different national lab at a slightly different scale, or something that it was, had different geographical locations, how repurposable is most of the what you're finding here?
So in terms of findings, I don't have any. I mean, Josh is probably way better positioned than me to answer a question like that. Certainly the tools we're developing should be sort of situation independent. They should be useful in any of those situations. How much beaconing there would be and so on in different organizations would vary, of course. But I think any of the tools we're looking at should have a general purpose use. But the findings across organizations, that's why I want more collaborators. So it'd be great to do some work with Microsoft, although you do more stuff on the host space, I know. But yeah, we need more collaborators. That'd be really good to see how these things vary between. Because it's not easy to share these sorts of data. LANL are very unusual in publishing these sorts of data. We don't have other open data sets, so I'm just an academic, so we have to work with
Has anyone other than Los Alamos kind of made that kind of about that?
I don't think so.
When you do your Fisher's G-test thing, like way back at the beginning, how did you pick the sequence of K values to test?
So it's just driven by how many time points I've got. And so the fast Fourier transform just naturally spits out the periodogram for all f in that range 1 up to floor of t over 2, where t is the number of time points I've observed. So I'm not in any way an expert on the mechanics of the fast Fourier transform, but I know there's an efficient algorithm which throws out S of f for all those frequencies simultaneously, really easily, much easier than doing them one at a time. So I don't choose it; it's what the algorithm automatically spits out, and it's great. It's really fast.
That test statistic, they had like a sum. Yeah, epic.
Mm-hmm. Yeah. Yeah. So these are the Fourier frequencies. That's what they are. These guys. These things here. So those are the ones that if you ask your favorite programming language to do the FFT, it will calculate this thing for these frequencies. That's just what it will return. So no, there's no choice from mine. I just get those for free without any effort, and it's super fast.
Like when you were modeling like the like the likelihood of like human traffic of like when it's going to occur. How are you filtering out like the automated traffic? Like we were like beforehand, were you already like determining like using the prior method like where what frequencies like the automated traffic was occurring at, and then like filtering it out and then doing that analysis, or
Right. Yeah. So. So for this stuff, there we're looking at edges which we've already sort of determined from those other analyses to be human ones, or the idea is that we would do a filtering step and perhaps, so it's all work that needs to be sort of pieced together. So there are links where it can also join together. So if we believe this sort of stuff where I can classify every single event as being human or automated, then I could take that filtered human data and fit these models on that. So that's the idea. But for the examples we use in this paper, I think we're using edges which, because the nice thing about doing the Imperial stuff is it's stuff from my computer and we kind of know the things, so we go, okay, that's a human one, we can sort of treat that.
so there's a way of like, I mean like there should be a way of like you being able to know beforehand like what polling things were going on or
Yes.
what devices that you
Yes.
have on, and then you would be able to like
Yeah,
get it,
true.
and then like
Yeah,
okay.
yeah. True.
So you mentioned, I guess, right here that the Poisson process is the pretty core model for modeling like human behavior
Yes.
on a network. So when you're looking at the adjacency matrix for like the entire network flow, is there a reason why you just use a Poisson process there? Because I'm assuming like traffic flow is a combination of human and automated. So could you like add the Poisson process and a Wold process there to model?
Sorry, I'm not sure what it is. So this part here is like a homogeneous Poisson process. So this is like the overlay of a homogeneous Poisson process with boosts. That's exactly what's going on. So there's a constant intensity. So yeah, it's like saying I've got homogeneous Poisson process, except I'm going to throw down some more points on top from this boost of self-excitation.
And that self-excitation is supposed to represent
The natural burstiness that we observe in the data, so it's somewhat an artificial contrast in the sense it's not like each event is triggering, although it could be, I suppose, in terms of firing off ads or so on. So maybe there could be a sense where it could actually be physically happening, but it's more just a way of trying to mathematically represent these bursts that we get by saying if I see an event, then I feel I'm more likely to see an event now in this next instant than I was before I had that initial one to get the sequence started.
But when you're doing the network flow, like looking at the entire network and encoding that in an adjacency matrix,
Right.
you're looking at each entry as just a Poisson process, right?
Oh, for the Poisson factorization stuff, yes, I see. Oh, good point. Yes, so we'll have some fairly inflated counts in that. So that's a very fair point. So, yeah, I can't remember that. I wasn't the person who actually did the actual analysis for that, so I don't know if any treatment was done in terms of truncating the data at all, and any factoring out of seasonality of automated stuff. There may have been some pre-processing going on, but I'm not sure. But it's a very good point. We should do that. Joining these bits together is sort of a bit that often sort of drops by the wayside, is to work on these individual projects and with the knowledge that they should sort of fit together, but whether that actually sort of gets done, I don't know.
Other questions? Let's, Jane, do you have some? No? Let's thank our speaker one more time.